Okay, hopefully this extra booklet got printed out. If not, we can just write down the answers in your exercise book and we'll give you a copy when we get it printed. So this is just a few extra examples on the triangle inequality and a few extra arithmetic mean, geometric mean examples. Okay, so let's start off here. So first one, prove that. Okay, so it kind of looks a little bit like the triangle inequality. But maybe you can notice that there's no absolute value on the right hand side. Well, maybe that's just relying on the fact that the absolute value of blob equals blob if blob is greater than or equal to 0. Okay, so we might need to justify later on why the right hand side is indeed greater than or equal to 0. So this just looks like a substitution into the triangle inequality type question, and a lot of triangle inequality questions are simply just substituting into the formula. Okay, so let's substitute x is equal to a squared minus ab, and let's substitute y is ab minus b squared, and see what happens. Okay, so you're taking a leap of faith here. Okay. Maybe it's not so much of a leap of faith if you think about adding these two bits together, what's going to happen. Alright, so let's go. What do we get? We get a squared minus ab plus ab minus b squared. And you can see that the ab and minus ab cancel nicely. So that's going to equal to absolute of a squared minus b squared. Which is absolute a plus b, a minus b. So we've got the question answer pretty much spot on, except we need to remove those absolute value signs. So we're going to have to use this condition, I think, to help us out. So I might just sidetrack a little bit and go, since a greater than b greater than 0, what can we say? So I can bring the b over. I can say a minus b is going to be greater than 0. So that second bit, the second bracket's definitely positive. And we also know that a and b are positive themselves, so if you add, that'll be greater than 0 as well. So I know that both brackets will be positive, so therefore a plus b times by a minus b will be greater than 0. Well, that's kind of nice. So I can basically say that because that is positive, I can remove that absolute value sign and say that equals to a plus b, a minus b, since a plus b, a minus b is greater than 0. Okay. So putting everything together, therefore we've proved our result that the absolute of a squared minus ab plus absolute of ab minus b squared is greater than or equal to a plus b, a minus b. Okay, that's that question done. Let's move on to another question. Once again, you can see the right hand side has no absolute value. However, the left hand side is the sum of two absolute values, so I am thinking triangle inequality again. And they've given us this condition which we might be able to use to simply remove the absolute value that would be here. Okay, well, clearly you can see that a minus c is greater than 0, so that'll work. So let's quote the triangle inequality, and we're going to substitute in. So let's go, x is a minus b and y is c minus b. I'm going to do it blindly, and we're going to see something interesting for this particular example. So substituting in, I'd get absolute of a minus b plus absolute of c minus b greater than or equal to absolute. And if you add the two, you'd get a minus b plus and then c minus b. Now, what's interesting here is if you look at this, this is not exactly what we want to get an a minus c. We want the b's to cancel. So we've got a minus 2b plus c. It's not what we want. So we've reached a dead end here for this particular bit. So rather than going on and approaching something new, let's have a think about how we can change this a little bit to be what we want. We want an a minus c. So essentially we want the b's to cancel out. So I've got a minus b there and another minus b, and I'm going to be adding, and they're going to be making a minus 2b. And the other thing I didn't like is I had a plus c and I want a minus c. So if you think about it, we need a simple property of absolute values, and I think this is going to be the key, right? This idea that the distance of c from b is the same as the distance of b from c, so therefore we can swap the two middle bits in the absolute value. That's going to be extremely useful. So let's use that. So absolute of a minus b plus absolute of c minus b is equal to absolute of a minus b plus absolute of b minus c. And hopefully you can see now when we add, the minus b and the plus b will cancel, and we'll be left with what we're after. So that's kind of nice. So that's by the triangle inequality, that's going to be greater than or equal to absolute of the addition of the absolute of the addition. Okay, so which is going to be equal to absolute of a minus c. Okay, and now we can quickly use this particular identity here and bring over the c, which is going to equal to a minus c as a minus c is greater than 0. Okay, you can write a greater than c, a minus c greater than 0. So either would be acceptable. You don't need to write both. You can write either one, and the examiner will understand that you know what's going on. So therefore, we've got absolute of a minus b plus absolute of c minus b is greater than or equal to a minus c as required. Okay, let's keep pushing on. So that's page 1 done. I'm going to move on to page 2. So we've got a triangle with 3 sides. And notice we're talking about triangle here. So begin to use the triangle inequality, and we've got sides of x, 10, and 12. What are the possible values of x? This is a very basic triangle inequality question. Recall, fundamental to the triangle inequality is the idea that the sum of any 2 sides of a triangle is greater than the third side. So if you have a triangle here, 10, 12x, I can say start from here and go to here and go, well, if I travel the 10 plus x path, that should be greater than traveling the 12 path. Notice I'm not including the equal to, because it must be a triangle. It's not allowing the linear case that that the lines are collinear. We can't, if they're collinear, it's not a triangle. So rearranging this, I would have that x must be greater than, if you minus 10, x must be greater than 2. Okay, and all I'm going to do now is I'm going to write the other 2 versions. So I'm going to start from here and go, say, to here. So from here to here, it should be clear that 12 plus x must be greater than the direct path of 10. So x must be greater than, if we minus 12, negative 2. Okay, and the last path that we haven't done yet, whoops, erase the whole triangle, is going from here to here. That 10 plus 12, the sum of those 2 lengths must be greater than the direct path of traveling x. So 22 is greater than x, so, or x is less than 22. So we got 3, from looking at the triangle, we got 3 inequalities, and all must hold. These are like intersections, they're ands. So x has to be greater than 2, and at the same time it has to be greater than negative 2, and at the same time it has to be less than 22. So if you combine those 3 things together, hopefully you can see that x must be between 2, and 22. Another way of sort of thinking about it geometrically is imagine you had your 10 and your 12 right sort of next door to one another, so that it was a very, very thin triangle. To connect and to close this triangle, x will have to be just slightly bigger than 2. So that's like the left hand side of the inequality there. And imagine the opposite case, the 10 and the 12 were as far away as possible, the 10 and the 12. To connect this, x will have to be, well, if it was perfectly flat, it would be 22, but because it's just not perfectly flat, it can be a little bit less than 22. So that's an alternate way of thinking about this particular question. Put the 10 and the 12 right next door to one another, or pointing right on opposite directions, and have a think about to close the triangle, what values must x be. But I like using the sum of any two sides of the triangle greater than the third. But that's just an alternate way of viewing. And just briefly, I wanted to show you an alternate proof for the triangle inequality that uses cases. So basically looks at, for real numbers, the triangle inequality. It splits it into cases. Basically relying on the definition that absolute value of x is x if x is greater than or equal to 0, or negative x if x is less than 0. So therefore it matters if we're greater than or equal to 0 or less than 0. So first case, let's make x and y both greater than or equal to 0. Then absolute values fall away. But also for the right hand side, because they're both positive, those absolute values fall away for the right hand side. So it's true if x and y are both positive. You actually get the equal case when x and y are both positive. And then you can look at x and y both negative. Doesn't have to be equal to, it can just be less than. So in the case that they're both negative, that absolute value of x will become negative x, and the absolute value of y will be negative y. So we get the left hand side is equal to negative x, negative y. And the right hand side here, if you got a negative added with a negative, that's negative. So when you take the absolute value, it's the negative of the whole thing. So you'll get negative and then bracket x plus y. So you get the equality case for x and y both less than 0. And then what you do is you consider one of them being positive and one of them being negative. So one of them, the absolute value will drop, the other one will become a negative. So we get x minus y. Now, I like visualizing things. So if you got x being positive and y being negative, when you add them, if you add them first, then absolute, you'll get this distance here. But if you absolute one, then absolute the other, and then add, you'll get a larger distance, which is why this works. Algebraically, let's see. So this step to this step should make sense, because y is less than 0. That's why it's negative y there. And because x is positive and y is negative, this whole thing is going to be positive. So we can absolute that. And we can say that, now, I'm trying to work out how they went from here to here. I think the key is that y is negative. Yeah, so if you subtract a negative, it's actually bigger than adding a negative. So subtracting a negative is bigger than adding a negative, and that's why we can go from there to there. Okay, so it's true for the case where, cross that out, x is greater than or equal to 0 and y is less than 0. So it's true for that case. And the fourth